So in this third part of substitution reaction, we are going to talk about an example of pharmacology, how they use organic chemistry principles in drug design. So pharmacology is basically study of the interaction of drugs with biological systems, and that helps us also to understand the mechanism of drug action, which ultimately helps us to design drugs. And today we are going to talk about the design of the drug called chlorambucil. It is anti-tumor agent and it's very powerful alkylating agent. So this is just the biological function and this is the chemical function. So alkylating means that it introduces alkyl group to the substrate. So origin of this drug, so we are going to have this story that I'm going to share with you, how we end up designing this compound that's used as anti-tumor agent. So origin is sulfur mustard here. It actually had been used as a chemical weapon in World War I. So they spray it as aerosol and it has mustard-like odor. Okay, it's a strong alkylating agent. And this is two-step substitution reaction. So in the first step, what happens is intramolecular SN2. Okay, even without any nucleophile, sulfur reacts with this center and chlorine leaves, and then nucleophile attacks. So here, sulfur lone pair acts as a nucleophile and chlorine acts as a leaving group. Then external nucleophilic attack. So the reason why we call it two-step substitution reaction is because first one is intramolecular SN2 and this is external. You can call it intermolecular, but this is just external SN2. But the thing here is that the net result is same as direct nucleophilic attack. It's like nucleophile replacing chlorine here. If you don't see a mechanism, it's like this. So this is actually faster than regular SN2, like primary. If you don't have any sulfur here, nucleophile would attack here and make chlorine leave. So that's what we call as direct nucleophilic attack. But this having sulfur here and having intramolecular nuclear SN2 prior to normal external nucleophilic attack actually makes this reaction much faster. And we call this as anchimeric assistance, also known as neighboring group participation. Here, what happens is that sulfur helps eject chlorine. So this is much faster than nucleophile attacking chlorine by itself directly. Since you have formed this three-membered ring here, it has a really high strain, so it really wants to be opened. So it's very susceptible to nucleophile attack. And that is the reason that contributes to this faster reaction in compared to the case where you don't have any sulfur or any intramolecular reaction. Okay? Chimeric assistance is really important. We will see the cases like this. So this sulfur mustard actually alkylates a strands of DNA. So that's the reason behind the toxicity of this gas. So I used mustard gas and that's how they're toxic and it's used as a chemical weapon. So these are the strands of DNA and these are just some bases of the DNA. And what happens is that it has two chlorine as leaving groups, so it can make two DNA alkylations and it would lead to cross-linking of DNA. So as you can see here, what happens is that the nitrogen here acts as a nucleophile and this nitrogen here also acts as a nucleophile, and then they basically replace chlorine. Obviously sulfur also participates in the mechanism as neighboring group. So sulfur attacks here, chlorine leaves. Yeah, nitrogen basically attacks and then opens the three-membered ring. And then the same happens for this nitrogen. And then basically you have the two strands of DNA, but now they are cross-linked to each other. And then this blocks replication. This is some kind of mutation. So when you have cross-linked DNA, it blocks the replication and it ultimately results in the death of the cells. Okay? That's why it is toxic, and that's the effect of mustard gas on the basically death of the cells. And this function of mustard gas as alkylating agent actually inspired its use as anti-tumor agent. So in 1931, they actually directly injected this compound into tumor cells so that can block the replication of tumor cells and then result in the death of the tumor cells. That way they wanted to prevent tumor growth. But then they find out that it's too toxic for clinical use, so they started to search for safer analogs. And the first analog is mechloroethamine. And that's actually less toxic than the sulfur mustard. Yeah, and then that also reacts via two SN2 steps, same as sulfur mustard. You see the same. So it actually have N-chimeric assistant. It ejects the chlorine leaving group. This is intramolecular SN2, and then nucleophile attacks, breaks the ring to alleviate the ring strain. And we basically, what happens here is that nucleophile reflex chlorine. So we basically use the same compound here, and then assume that these are the DNA of the cell, tumor cell, and then they are going to cross-link it, and then they are going to block replication, and then tumor growth will be prevented. That actually is the birth of chemotherapy, where they use chemicals, inject the chemicals into patient's body, and then that blocks the replication. And that's how they have found out that, oh, there could be a field of chemotherapy where we can inject chemical compounds, and that they can interfere with the DNA replication or any kind of tumor cell growth. They can interfere with the process or some kind of metabolic pathways, or there are a lot of ways where that different chemical affect the tumor growth cells in a different way chemically. It could be metabolic pathway, it could be something like introducing mutation into DNA so that it can block its replication and ultimately result in cell death. So there are a lot of ways, and this is just the first instance where they have inspired from mustard gas, and then they have found out that, okay, you can use less toxic compounds that could tumor growth. Then there's a problem because this is less toxic, but it has high reactivity with water. Chloroethanamine is still used with combination with other reagent. We call them combo therapy for treatment of some other diseases. But because of its high reactivity with water, it led to search for better analogs. What they did is they replaced methyl group with aryl group. Okay, aryl group here delocalizes lone pair via resonance. As you can see, this lone pair on top of nitrogen is actually in allelic position. So this allelic lone pair, and it can basically negative charge can go on top of carbon and another carbon here and then another carbon. So you basically make, this is just the amide. So you have amine and then amide. When you compare them, you will find out that the lone pair on the amide is actually less basic, less electrophilic. Why? Because it can delocalize onto oxygen. This is the similar story here. And here the ultimate result is that lone pair becomes less nucleophilic. And then that gives the slower, more controlled reactivity with water. And then this is obviously less reactive with water, so it's more stable compound. So as you can see here, resonance structure have the negative charge on carbon. So they are all minor contributors. So if we try to assess the significance of the resonance structure here, all of them are actually minor contributors. This is major contributor, and we still have this acting as alkylating agent, but then it's less nucleophilic. So because nitrogen lone pair is delocalized over aryl group, that makes lone pair less nucleophilic, and that results in decreased N-chimeric assistance. But then we still have N-chimeric assistance, but decreased N-chimeric assistance. So it's still active as anti-tumor agent, but with slower water reactivity. So basically, replacing methyl group in mechloroethamine by aryl group solves the problem of high reactivity with water. But introducing, and then obviously we don't want it to react with water, right? So it can be, because it would deplete the water resources in patient's body. So that's the reason why we are having this. But at the same time, it should be soluble in water because we administered the drug, right? We inject it to human body, so it should be soluble in the drug. But replacing methyl with aryl, actually, even though it fixed water reactivity issue, it caused poor water solubility. So it blocked the administration of the drug. So in order to solve this problem, we have to introduce carboxylic acid group. Okay, we still have aryl group so that the nitrogen lone pair can delocalize and decrease the N-chimeric assistance, which decreases the reactivity with water. But at the same time, we are introducing COOH, which solves the solubility problem. But it introduced another problem. We would have excessive delocalization. So in addition to this lone pair being delocalized onto 3 carbons, it's going to be delocalized onto 2 oxygen here, you will see. So oxygen. Then negative charge on oxygen, more stable than being on nitrogen. This is going to be major contributor. Okay, and then we will no longer have nitrogen lone pair acting as a neighboring group, participating as like in a mechanism. So basically, too much delocalization here will result in no n-chimeric assistant and it will lose its anti-tumor activity. So do you follow the steps here? So what we did is we replaced sulfur so that it's less toxic. Then it was reactive with water. So we replaced this methyl group here by aryl group. But then it was poor soluble, so we introduced carboxylic acid to make it soluble in water so that we can administer the drug efficiently. But then it resulted in extensive delocalization, ultimately losing anti-tumor activity. So in order to solve this problem, we are adding methylene group. This is the solution that they came up with in order to make sure that there is no further resonance, but it's still water soluble. So by having so this CH2 group is, by the way, called methylene group. So by having group, prevent over-stabilization, we prevent over-delocalization, but at the same time we maintain water solubility. So here, nitrogen lone pair is not in resonance with COOH, so this prevents over-delocalization, and carboxylic acid still ensures water solubility. So theoretically, minimum number of is just 1. Even if you have just one methylene group, you could achieve this between water solubility and extensive delocalization. But they have found out that practically 3 methylene groups is optimal for the best reactivity. And the resulting compound is chlorambucil, and it's currently mainly used for treatment. This is just one disease, CLL, and there are also some newer agents for tumors. Okay. This is the of drug design that integrates pharmacology with organic chemistry principles. And so basically organic chemists and biochemists together, they drive advances in pharmacology and drug design. So this example shows that how basic principles that we learn in organic chemistry helps us to advance pharmacology to come up with better drugs designs. Okay. Lastly, we are going to talk about nucleophilic strengths. So first, we have to define what is nucleophile. Nucleophilicity is a rate at which a nucleophile is attack an electrophile. So nucleophilicity is basically kinetic concept because it's directly related to rate. For example, I have a strong nucleophile and weak nucleophile. The only thing that differentiates strong nucleophile from weak nucleophile is it's in the rate. It is the rate of the SN2 reaction or rate of the substitution reaction, where nucleophile, how fast nucleophile reacts with alkyl halide. So in this case, OH minus is faster, reacts faster with methyl halide, methyl iodide. So OH minus is stronger in compared to water, which is very slow with methyl iodide in SN2 reaction. Okay, how we can, so this is the definition of nucleophilicity, but how we can find out the factors that affect nucleophilicity. So there are 2 factors. First is the presence of charge. The second is polarizability. I think presence of charge is quite reasonable in compared to having just lone pair. Having charge makes it more nucleophilic. But what is polarizability? We define polarizability as ability of atom to distribute electron density even unevenly when you have some external influences. And that is directly related to size. Larger the size, more number of electrons that you can have distant from the nucleus, so you can basically unevenly distribute electron density. And that makes the nucleophile highly polarizable, which makes it ultimately more nucleophile. For example, sulfur and oxygen. Sulfur is larger than oxygen, so sulfur is actually much better nucleophile than oxygen. So here is the simple table and table of nucleophiles that we will encounter in this chapter when we talk about substitution reaction. In bromine, chlorine, like typical halides, they are very strong nucleophiles, and sulfur and oxygen, they are also strong nucleophiles, but then you don't have any charge here, water and alcohol, so they're actually very weak nucleophiles. And here we have all halides except fluorine. Reactivity, fluorine nucleophilicity actually depends on the solvent, and we are going to talk about solvent effect at the end of the chapter. If this video gave you at least one aha moment, a like or subscription would mean a lot, but only if you think it's worth it. That's the only kind of support I want. Genuine. Thanks a lot and take care.